In the last discussion, we highlighted the ellipsoid, geoid, and datum and their significance in spatial representation. In this part, we would discuss the coordinate system. Here, it can be a simple spatial reference arbitrary system, such as 20 meter by 20 meter grid, or even more commonly, like a football field. But in terms of spatial representation, this football field needs to be based on some Earth reference system. This can be a geographic coordinate system. So locations on the Earth's surface are measured and represented in terms of coordinate. Methods of assigning a unique index to mapped locations, typically in the form of an east-west value or a north-south value, and possibly also an elevation value. The coordinates are used to identify locations on the Earth's surface, and locations may be relative to Earth's surface or may be displayed in that way. So a coordinate system is a set of two or more numbers, digits, that specifies the positions of a point or a line or an area or a geometric figure in relation to some reference system. That is what the coordinate system, that is what the objective of or use of coordinate system. The simplest system of this kind is a Cartesian coordinate system, named after the mathematician and philosopher Descartes. A graph paper is a good example of this Cartesian coordinate system. A Cartesian coordinate system is simply a grid formed by two measurement scales, one horizontal, the x-axis, and another is vertical, which is represented by y-axis. The choice depends on size of area of interest or standardized coordinate system. The point at which both x and y equal 0 is called the origin of the coordinate system. Again, I would say a good example of it is the graph paper. When we draw any two-dimensional graph representation resembles with the Cartesian model system of coordinate system. In this figure, the origin 0, 0 is located at the center of the grid, as I was saying, and all other positions are specified relative to the origin. In this diagram, the coordinates of upper right hand corner of the grid, which is being put as a dot, can be read as 6 on the x-axis and 3 on the y-axis. Similarly, the lower left hand corner is representing -6 on the x-axis and -3 on the y-axis. The Cartesian and other two-dimensional plane coordinate systems are handy due to their simplicity, and that is why they are very popular. However, they are not perfectly suited to specify geospatial positions where we are representing the spatial information which we want to represent in flat plane, but we are converting the spherical shape Earth phenomena onto flat plane. So they may not be perfectly suited with the Cartesian coordinate system. It represents the rectangular or planar coordinate system. This diagram, it represents the rectangular or planar coordinate system which I am discussing in the context of Cartesian coordinate system. So as I have said that the Cartesian coordinate system may not be very perfect for representing the spherical Earth shape. So we require a coordinate system in order to locate points more precisely, because we are dealing with spatial information of the Earth phenomena, as well as measure distance and direction also required to be very accurate. So a coordinate is a number set that denotes a specific location with a reference system. A coordinate system is often structured in a two-dimensional or three-dimensional plane also, that consists of a set of reference points that define the spatial position of a point. So method of assigning a unique index to mapped locations, typically in the form of an east-west value and a north-south value, and possibly an elevation value also. The coordinates are used to identify locations on the Earth's surface. Locations may be relative to Earth's surface or map display. The choice depends on the size of area interest. And that is why there can be two types of coordinate system. One is geographic coordinate system, and another one which we have already discussed in Cartesian coordinate system, which can be termed as rectangular or planar coordinate system. Moving ahead, focusing on a geographic coordinate system, that is a reference system for identifying locations on the curved surface of the Earth. Locations on the Earth's surface are measured in angular units from the center of the Earth relative to two planes. Generally, we refer to latitude and longitude. So in this diagram, you can see the Earth's parallel, the latitudes, the meridians, that is longitude, and origin of geographic coordinate system. A three-dimensional coordinate system that enables every location on the Earth to be specified by a set of numbers, as I am saying, in the form of latitudes that are horizontal and longitudes which are vertical. Locations on the Earth's surface are defined by three numbers: latitude, also known as parallel, longitude as known as meridian or longitude, and also ellipsoidal height. It is the primary system and is used for all basic mapping such as navigation or basic surveying or representing spatial information. When I am saying spatial, that is, it corresponds with any specific location over the Earth's surface. So this geographic system is useful for locating positions on the curved surface of the Earth. A latitude measures the angle from the equatorial plane to the location on the Earth's surface, whereas a longitude measures the angle between the prime meridian plane and the north-south plane that intersects the location of interest, which is very clearly depicted in this diagram. The geographic coordinate system is defined on Earth's three-dimensional ellipsoid through a series of horizontal and vertical lines, that is, the latitude and longitudes. Longitudes meet at the pole, which you can see in this diagram. They are often called as meridian. The horizontal lines are called latitude. So latitude lines are parallel to each other and therefore often called as parallels. So here, moving ahead with the same diagram, the Earth's parallel intersects every meridian at right angles. The central parallel located exactly between the poles, which is commonly called as equator or 0 degree latitude. The central standard parallel holds a latitudinal value of 0 degree. The remaining parallels are assigned angular values relative to their direction and distance from the equator. So 80 degree, 90 degree north latitude would be representing the North Pole, and as we move towards the south, away from the 0 degree latitude, that would be representing the southern hemisphere. So equator lies in between the northern, it separates the northern hemisphere and southern hemisphere, and it is represented as 0 degree latitude or equator. The diagram of geographic coordinate system showing latitude and longitudes clearly points towards the lines of latitude progressing towards the North Pole are assigned parallel ranging from 0 to 90 degree north. Likewise, the lines of latitude progressing from the equator towards the South Pole are assigned parallels ranging from 0 degree to 90 degrees south. The same way with the north-south line grids, with 0 degree passing through Greenwich in London, with a total 360 vertical lines which are converging on poles over the globe. The Greenwich meridian is called as the prime meridian and holds a longitudinal value of 0 degree. The lines of longitudes progressing eastward from the prime meridian, I mean to say from Europe, from London, eastward towards Asia, they are assigned longitudes from 0 degree to 180 degree. Otherwise, we also take plus 180 degree towards east. The lines of longitude progressing westward are assigned longitude 0 degree to 180 degree west. Otherwise, also it may be called as minus 180 degree. So, if we move eastward from the prime meridian, we take it as plus longitude degree, or we add the suffix of east longitude, and when we move westward we take the suffix of west longitude, or we mark them in negative values. Just to summarize the geographic coordinate system, here in this figure, the point P has a latitude of 30 degree north and longitude of 20 degree west. The parallels of latitude, they are all small circles except for the equator. They are true east-west lines, always parallel, and these parallels are related to the horizontal x-axis if you consider it in the Cartesian coordinate system. Whereas meridians or longitude, they are halves of great circle connecting one pole to the other, all run in a true north-south direction, spaced farthest apart at the equator and converge to a point at the poles. Meridians are similar to the vertical y-axis of the Cartesian coordinate system. But significantly, the projected coordinate systems induces errors in their geometric measurements. It has to do with the nature of projection, whereby the distance between 2 points on a sphere or ellipsoid will be difficult to replicate on a projected coordinate system unless these points are relatively closer to one another. Now here I would refer to my previous discussion with you, where I have highlighted the different projections and the distortions which were visible in the discussion. So this geodesic geometries are very important. In most cases, these errors can be tolerated if the expected level of precision is met. Many other sources of errors in the spatial representation of the features can often usurp any measurements errors made in a projected coordinate system. So a geodesic distance is the shortest distance between 2 points on an ellipsoid or spheroid. Likewise, a geodesic area measurement is one that is measured on an ellipsoid. So if the scale of analysis is small, that is, the spatial extent covers a very large area of Earth's surface, such as the entire continent like Asia or America, then the measurement error associated with a projected coordinate system may be significant enough to ignore. But if we are taking a large scale map, then these areas would be very much projected and we cannot ignore them. So this diagram would show you what I mean. The distance measured between 2 points located on the two sides of Atlantic Ocean in this map, the blue line represents the shortest distance between the 2 points on a planar coordinate system, whereas the red dashed line represents the shortest distance between the 2 points as measured on the spheroid. So that's very interesting. At first glance, the geodesic distance may seem nonsensical given its curved appearance on the projected map. However, this curvature is a byproduct of the current reference systems increasing the distance distortion as one progresses polewards. So in the previous diagram, here you see it is not this one, this one. Here you see it is far more, but here it is the distortion when we move towards pole, it is far greater. So in many cases, a geodesic approach to spatial operations can be perfectly acceptable and is even encouraged. This is because geodesic calculations have no simple algebraic solutions and involve approximations. They may require iterative solutions. The challenge is in its computational requirements. It's far more computationally efficient to compute area or distance on a plane than it is on the spheroid. So this may be computationally taxing approach if processing millions of line segments, because this example is only between 2 points. But when we are spatially representing any point location or any linear feature or any area feature, then we have to take into consideration many line segments, and then it becomes very tedious and very taxing. However, not all geodesic measurements implementations are equal. Some are efficient algorithms that minimize the computation time, may reduce precision in the process.